All right, so the video I was talking about is going to be the slide after this one, where they actually show this happening, and that's really, really cool. Well, it's not protons they use electrons. This problem's about a proton, but the concept's the same. They fire a beam of electrons into a uniform magnetic field that they created using coils like solenoids, and the magnetic field causes this beam of electrons to bend into perfect uniform circular motion. And they actually make it so that you can actually see the beam of electrons. So I thought that was really cool. So yeah, that's what this problem is about. They give you some variables and ask you to solve for a specific variable. So they ask you to solve for the B value, how strong the magnetic field is. So what I've written down is the formula from the previous example. That's the force felt by the moving charge in a magnetic field. And the big concept here is that this force is actually a centripetal force. This force is actually a centripetal force as long as the charges were fired in at a 90-degree angle to the magnetic field, which we assume they are. So sine of 90 equals to 1. So I'm actually going to erase that term. Okay, we'll make that assumption. So assume the velocity and the magnetic field are perpendicular. Then the charges will move in circular motion. So we actually go back to Unit 1 and think about our centripetal force formulas. So centripetal force will be equal to mass times the centripetal acceleration. And the centripetal acceleration has a formula of v squared over r. And then both sides of the equation have a v in it, so 1v can cancel out. Leaving us with this expression here. So this expression is a 5-variable equation. There's 5 different variables, and this is how they're all related to each other. For the special situation of a charged particle, a moving charged particle, being caught by a magnetic field and being put into uniform circular motion. So just a little bit of review on circular motion. We've done many examples with different types of forces providing the centripetal force. So for a planet going around the sun or a moon going around the planet, the centripetal force is provided by gravity. When I was spinning that plate around with a rope, the centripetal force was provided by the rope, the tension. For a car going around a curve in the road, the centripetal force was provided by friction. So there's all sorts of ways to provide a centripetal force. So for this specific situation, the centripetal force provided onto these charges is the magnetic field, the magnetic force. And so I thought that was pretty cool. So various problems that you may see in your homework or maybe in an upcoming problem set will really come down to this equation that we have in the box here. You're not allowed to just start right at that equation when you're writing a solution. I would like you to start way at the beginning and kind of derive this equation. The equation will get a little bit bigger later next week when we talk about electric fields as well. Yeah, that's the main focus of next week is electric fields. But this is the equation for now. For this specific question, we're asked to solve for the magnetic field. So I'll just rearrange it for B. That's just going to be dividing both sides by Q. So I'll put in the values. So the mass of a proton, you got to look that up from the useful values document. The velocity is given to us at 2.0 times 10 to the 4. The charge of a proton, you can also find that in the useful values document, 1.60 times 10 to the negative 19. And the magnetic field, the radius is 30 centimeters, which needs to be put into meters, the SI units, so 0.30. Okay, so I'll go to my calculator, and so 1.67 times 2 divided by 1.6 divided by 0.3 gives me 6.96, or 7.0 if I go to two significant figures. And now I'll do my exponent laws. So 10 to the negative 27 times 10 to the 4, that makes 10 to the negative 23. Divide that by 10 to the negative 19, that makes 10 to the negative 4 overall. And the units would be whatever the SI units are for a magnetic field, which are Teslas. And this result seems kind of reasonable because Earth's magnetic field is like 3 or 4 times 10 to the negative 5. So this is more than 10 times stronger than it, which is kind of what we want. We want it to kind of dominate. All right, so hope you enjoy the video on the next slide, even though it's just 2 minutes, but you can see a beam of electrons getting bent into a circle by using a magnetic field.